All right, let's begin. First reminder is the Writing Center appointments. You need to have those done by Sunday of next week. I've started to get the reports. Anytime you go to the Writing Center, I get an email report, and so those are starting to roll in. I've posted the comments and the scores online for your first draft, and I was really happy with those. So keep up the good work, and if I had specific comments, just look in the grade book where I entered those for you. Yes? The handout that I've given you shows what all the total grading is, because the grading includes the appointment that you go to, the draft submission, and the final paper. And so there's points at every stage, every aspect of what you're supposed to do. Homework 11 is due on Sunday, and I've handed that out to you today. Maybe you guys can do the rest of the paperwork stuff after class. And we have an exam a week from today. I'll give you more details about that when we meet on Thursday. We're going to continue talking about secondary treatment today, and specifically activated sludge. There's another kind of secondary treatment that it's called attached growth, and we'll do that on Thursday. So let's just sort of review where we left off last time. We're talking about how the microorganisms can be tricked into eating a lot of food inside of the treatment plant so that they don't do it in the river. It's bad if they eat a lot of food in the river, because then it depresses the dissolved oxygen and will start to kill fish. So it's just best for us to take control of the situation and provide plenty of oxygen and a special place where the BOD can be broken down. This is a schematic of what it would look like if we didn't have recycling of the sludge. Does anybody remember why we do want to have recycling of the sludge? Like, how is that beneficial? Yes? Good, right. Remember what we talked about last time was, for us to break down all of that substrate, S in this diagram stands for substrate, and that's another word for food. And the food of the bacteria is their BOD. So we want them to eat as much of the substrate as possible. By re-injecting hungry bacteria, that's going to make the reaction a lot faster. So this is showing what would happen if there was no recirculation of sludge. And there are a few treatment plants where sludge recirculation doesn't happen. In fact, there's some here in the UAE where they don't have recirculation. And when that's the case, you have to have a very, very large tank, because the mean cell residence time is the same as the hydraulic residence time. Remember, what we're doing is we're keeping track of separately how much time the cells spend in the system and how much time the water spends in the system. Well, when there's no recycle, they spend the same amount of time. The cells just pass through along with the water if there's no recycle. And so this mean cell residence time, theta sub c, sometimes it's called the detention time or the sludge age. That's just the average amount of time that one of the bacterial particles will spend inside of the reactor. You'll notice here that we're assigning the variable x to something called the biomass concentration. And sometimes we also refer to it as mixed liquor suspended solids. And that's abbreviated MLSS. And occasionally we'll have mixed liquor volatile suspended solids, MLVSS. And the two are almost identically the same. The volatile suspended solids are the ones that would be burned away if we put it into an oven at a high temperature. And the bacteria fall into that category. They are the microbes. And so we're keeping track of the flow rate Q, the food concentration S, the biomass concentration, and then the volume of the reactor is V. And this isn't a very useful configuration because we have to make the tank so large to have the reduction in BOD. Here is the formula for how we would calculate the cell residence time when there's no recycle. Like we've said, this has poor control over the microbial population. We don't get to adjust how many are inside of the tank if they're just passing through naturally. And because of that, the reaction is slow and the tank has to be too large. And so this is kind of a rare thing to have no reinjection of sludge. The one instance that it is used commonly is in rural areas where there's lots of free land. Not free as in no cost, but means it's available land. They'll just have a big pond where they put all the wastewater and they sort of let it naturally attenuate, naturally aerate. And those are called aerated lagoons. Those aerated lagoons are very uncommon for cities and more populated places. Okay, this is the diagram that we're going to sort of focus on and solve problems with today. It shows the water flow rate Q coming in with an initial substrate concentration. And so the 0 in the subscript means the initial amount. So the initial amount of food, it comes into the aeration tank, and you can see the aeration tank is well mixed. It's also receiving oxygen. And so the parameters we have to keep track of is X, which is the concentration of bacteria, S, which is the concentration of food, and V is the volume. How come S naught is different from S in the aeration basin? How is that possible that the inflow concentration isn't the same as the concentration inside the reactor? Yes? As soon as it enters, it's mixed and the bacteria are eating what's in there. So it's not that all of the BOD is instantly consumed, but it's instantly diluted because it's a well-mixed reactor. Remember, this is a completely mixed flow reactor, CMFR. And when the BOD comes in, it's instantly spread out. Now, they're not efficient as a plug flow reactor. Remember, when we have first order kinetics, we've talked about plug flow reactors versus completely mixed flow reactors. But they're easier to operate than a plug flow reactor. And so it's more common to have an aeration basin acting as completely mixed rather than plug flow, just because of ease of operation. Here's our clarifier. The solids settle. We waste some of the sludge. That's what W stands for here. Wasting some of the sludge and recycle some of it. X means the concentration of bacteria, the mixed liquor volatile suspended solids. R means the recycle stream. And you'll notice that the concentration of bacteria that we waste is the same as the concentration that's being recycled. It's just how much bacteria is in the sludge that's settling. And we have a different flow rate, Q sub R. The recycle flow rate is different from the inflow liquid flow rate. So we'll keep this sort of diagram in the back of our head as we go through some problem-solving procedures. When you are an environmental engineer, there's a lot of things you can't control. And there's just a few things that you can control. And what makes it even more frustrating is that you have to make decisions very, very early on how big things are going to be. Treatment plants are generally made out of concrete. And so it's not easy to adjust the size of a concrete aeration basin after it's already been built. It's not like they're movable walls. And so the design parameters are things that you have to analyze at the end of the service life. What are going to be the demands of the system? How much water's coming in when the city is fully constructed? What will be the BOD when there's industry, factories, food processing plants? You have to understand the conditions at the end of the design life. So let's go through a list of design parameters, and then there's also one operational parameter that we can control after the treatment plant is built. So we get to design how big the reactor is, and by reactor what I mean is the aeration basin. So that's one of the things we can adjust, and however big the reactor volume is, that changes how long the water spends inside the aeration basin. We don't control the flow rate. The people flushing the toilets control the flow rate. We can kind of equalize the flow rate. Remember, with the flow equalization basin, we can smooth out the flow so that there's less peak during the day, but that's still, on a 24-hour basis, it's not accumulating anything. It's just sort of averaging it out a bit. We can design what we expect the sludge recirculation rate to be. And that is how much of the sludge gets sent back into the reactor versus how much of it is wasted. We have to have an idea of that when we do the rest of the design. And how much sludge we recirculate is going to affect the ratio of food to microorganisms. We want to make sure that there's enough microorganisms to eat all the food that's in the solution. Yes? What that means is that if you have 1 cubic meter per second of water coming in, then we would have 0.2 cubic meters per second as the recycle. So it's talking about Q sub R versus Q. That 20 to 30% is the ratio of the flow rates. We have to provide oxygen to all the bacteria, because if they don't have enough oxygen, they're not going to be able to continue eating the food. And so we have to design diffusers and an aeration assembly that provides all that oxygen. And sort of a rule of thumb is that for every cubic meter of wastewater that's being treated, around 8 cubic meters of air has to be injected and diffused. Not all of that air is going to dissolve, only a small fraction of it. And that's why we have to provide an excess. One of the things that we have to keep in mind is how good is the secondary clarifier at settling solids. And we have to make sure that it's very good, because we want those solids to go re-inject into the aeration basin. So if the clarifier downstream of the aerator isn't doing its job, then we won't have the sludge we need to re-inject. And finally, this operational control is the one parameter that after the treatment plant is built, we can still go back and adjust. So if we look at this diagram, there is a valve here at the junction of where the sludge is deciding if it's going to be recycled or wasted. So there's a valve, and we can decide how much of the flow is wasted versus how much of the sludge is re-injected. So as the conditions change inside the aerator, we can either decrease or increase how much microorganisms is going back into the aeration basin with that one operational parameter we get to control, which is how much is wasted. All right. So here is a formula that we'll use to calculate what is the ratio of food to microorganisms. Remember, food is BOD, and the concentration of BOD coming in is S naught. And so if we multiply the flow rate by the concentration, then that gives us the milligrams of BOD per day that's entering the reactor. So the food is on a mass per time basis. And then the amount of microorganisms is the volume of the reactor, the aeration basin, the volume of that multiplied by X, which is the concentration of microorganisms. And so this is going to tell us how many milligrams of mixed liquor volatile suspended solids. And by the way, liquor is a strange thing to call this. I think that means sort of like a mixture, or when sanitary engineering was first being developed as a field, they thought of this as like a concoction. And so I think it's just the same language is used for the liquor that people drink when they're getting drunk. It would be even worse than getting drunk if you drank this liquor. It'd probably kill you. So food to microorganisms ratio. This is what we'll use to calculate that. And we can control it by how much sludge is wasted. That one valve that we get to decide whether the sludge that's coming down the pipe is wasted or recycled, and the ratio of the two. If we waste a lot of sludge, so we're getting rid of extra bacteria, then that lowers the amount of mixed liquor volatile suspended solids that's present. So the microorganism goes down, and what that's going to do, if you think about low M, that increases the ratio, because there will be more food for every microorganism that's present if you're having very little microorganisms be re-injected. A high F to M ratio means every organism has so much food. A low F to M ratio means that the organisms, relatively speaking, are starved, that there's a big population and not enough food. And what happens if the population is starved is that they start to become very efficient. They eat every scrap that's available. Sort of like you know, if you have a chicken, first you start going for like the meat that's easy to get to. But when all of the food is gone, if there's a lot of people, they'll clean every bone, get every little morsel of meat off of the chicken. Well, if you have a low F to M ratio, the bacteria are doing something similar. They're not just breaking down the simple carbohydrates, they're finding every possible little scrap of energy that can be broken down in that wastewater, and they're being more efficient and they're degrading the waste more completely. And so what corresponds to a low F to M ratio is if the cells are in that recycle system a long time. So a long mean cell residence time maybe would be as long as 10 or 15 days that the average cycle is, that the average cell is spending in the secondary treatment. If we look at it in terms of food to microorganism, 1 milligram of food per milligram of suspended solids per day would be a lot. And think about that. How much do you weigh? Maybe like 70, 80 kilos, right? So what if your food to mass ratio was 1? The bacteria, what that means is, what if you were eating 70 or 80 kilograms of food every day? And that would be a lot, right? We can't do it. The bacteria, they have a bigger appetite than we do. And so the bacteria are eating between 0.1 to 1 milligrams of food per milligram of body weight. So they're very good at eating. They're good at what they do. They're eating and dividing. They're eating and dividing. And that's part of the reason they can do it, is that they're doing the binary fission very quickly. And so the population is growing. Here are the design equations we're going to use in an example I'm putting on the board in just a moment. We go through them step by step. We start, when we do our design, of considering the detention time of the liquid, then the detention time of the cells. We calculate what detention time corresponds to a certain outflow concentration we need, and so on. This table that's shown in the lower right is some kinetics data. And you can get this kinetics data by going to a table like this, or if you're setting up a treatment plant for the first time in a city, they would usually do some bench studies and try and take samples of the wastewater and study it to find out how quickly the BOD is breaking down food, how quickly these types of bacteria are growing, what's their death rate, and so on. So mu is the maximum growth rate, and then we have the growth rate when they have half of the maximum growth rate. A decay coefficient is about how quickly the bacteria are dying. And then the yield is a ratio that tells us for every kilogram of food they eat, how much weight do they gain. And that's another thing that the bacteria are good at, is they're very good at turning food into weight gain. Humans, it seems like we're good at it, but we're not. If you eat a kilogram of chocolate, you're not going to gain 1 kilogram. You'll use some of that energy and burn it off. But the bacteria are much better at turning food into body mass. And the reason why we like that is the food they're eating, remember, is dissolved BOD. We have no way of getting dissolved BOD out of solution other than turning it into something solid that will settle. Okay, I'm going to illustrate this calculation on the board. I'd recommend you take good notes because this is the exact thing you're going to do for the homework assignment. What we have is a treatment plant that is designed to have an inflow Q of 0.25 cubic meters per second. So 0.25 cubic meters per second is the flow rate coming in. And its limit is suspended solids can be 25 milligrams per liter. 25 milligrams per liter. The BOD5 limit is 30 milligrams per liter. BOD can be in two places. The BOD can be suspended particles and then dissolved. All right. What we want to find out as our first step is how much can be the suspended concentration in the aerator. Some other information we have, we're going to use the typical growth constants from this previous table. This table has, in this far right column here, typical values for each of the parameters that we need for kinetics. And so let me write that on the board. Our typical Ks is 60 milligrams per liter of BOD. Mu sub m is 5 inverse days. K sub d, the death coefficient, 0.06 days to the minus 1. And then our yield we're going to use is 0.6 milligrams of VSS per milligram of BOD that's removed. All right. Here, the letter S stands for substrate. That means BOD. Our limit that it says here, 30 milligrams per liter, that's the total BOD. The total BOD. So BOD allowed is 30 milligrams per liter, and that means both the soluble and the suspended. So BOD soluble plus BOD suspended. It says in the problem statement that suspended solids is 65% BOD. That means the little particles that are going to be discharged to the river, we're allowed to have 25 milligrams per liter of those particles, but those particles are part fixed solids and part of them are volatile solids that have a BOD. And so we want to account for that. The suspended BOD is 0.65 of the 25 milligrams per liter. And so that is 13.75 milligrams per liter. Now we're allowed to have 30 milligrams per liter total, so the S, which is the soluble BOD concentration, is going to be 30 milligrams per liter minus 13 point, hold on a second. I think my final answer is 13.75. What's this one? Thank you for checking that. 16.25 milligrams per liter. All right, so 30 minus 16.25 milligrams per liter equals 13.75 milligrams per liter. Okay, so back to the beginning. There's two parts. They're suspended and dissolved. And this is the dissolved BOD concentration that we call S. The total BOD is going to be accounted for in both. Okay, so that's part A. Part B. What is the mean cell residence time? We use this equation to calculate the mean cell residence time. And so we'll just substitute in all of the known parameters. We have 13.75 milligrams per liter of BOD. We have 60 milligrams per liter for the K sub S. For K sub S. Then we'll have 1 plus 0.6. And that 0.6 is unitless just because it's a yield. It's mass per mass. So it's a fraction. Times theta sub C, which is unknown at this point. K sub D, right, okay, thank you. Yeah, you guys are helping me out today. 0.06. Okay, did everybody have that? So 1 plus 0.06 times theta sub C. Theta sub C is also in the denominator, and then we have 5, and the units on 5 is days to the minus 1, minus 0.06, and then minus 1. Okay, so if we rearrange that, it works out to 67.925 theta sub C minus 13.75 is equal to 60 plus 3.6 theta c. Theta sub c is 73.75 divided by 64.325, 1.146 days. That's how long the cells are spending in the recycle system before they're discharged. That's pretty short on the spectrum of possibilities, but that's what we need in order to achieve the outflow substrate concentration. Okay. I'm going to blank out the screen so I can use the rest of this whiteboard. You've got the slide in front of you that has the formulas. All right, part C, what is theta? Okay. Part C. We're using the formula x equals theta sub c times y s naught minus s theta times 1 plus kd times theta c. We can rearrange that to solve for theta. And what we do, it gives us theta is theta sub c times y, s naught minus s, x 1 plus kd times theta c. Okay, and then we'll make the substitutions from there. We'll put in the theta sub c we just found, 1.146 days, and 0.6 for the yield. 115 milligrams per liter is the inflow concentration of BOD. 13.75 milligrams per liter is the outflow concentration. The mixed liquor volatile suspended solids is 2,500 milligrams per liter. 1 plus 0.06 inverse days times 1.146 days. Okay, so we're just substituting in all of the kinetic parameters we already have along with the given inflow, outflow concentration, and the theta sub c we just barely calculated. Okay, so that gives us a theta. It'll be 69.6195 divided by 2671.9. It's very short, 0.026 days, which is 2251 seconds. That's the hydraulic detention time inside of the tank. Okay, that was part C. Part D, the aeration basin volume required. We're calculating the volume of the tank. It's going to consider the volume is Q times the hydraulic detention time, 0.25 cubic meters per second, multiplied by the 2251 seconds that the water has to spend inside of the tank, then it should be 563 cubic meters. And then finally, E, if we have the concentration of return sludge, what's the waste flow rate? All right, so the sludge waste rate. The given formula is theta sub c is the volume times x QW times XR. We can rearrange that to solve for the waste flow rate. Q sub W is V times X theta sub C times X sub R. Okay, we'll put in the volume of 563 cubic meters. The concentration of mixed liquor, 2,500 milligrams per liter. The cell residence time of 1.146 days times the recycle concentration. In the problem statement here it says that the return sludge, mixed liquor, volatile, suspended solids is 6,000. So the concentration in the return is higher than inside the aeration basin. So 6,000 milligrams per liter. That tells us how much sludge we need to dispose of, 205 cubic meters per day. That's a lot of sludge. Any questions on this illustration? You'll go through the same process in the homework assignment where you'll need to rearrange some of the equations to solve for the parameter that you're studying, but there's one assumption that this makes. These equations are assuming that here that there's no cells that are being discharged. The equations that we've just gone through today are a little bit of a simplification, assuming that x sub e is 0, assuming that the clarifier is 100% efficient at settling the solids downward and that none of the mixed liquor is getting into the effluent. When that's not the case, there are more complicated equations we can use, but generally those aren't needed at this level. All right. So some other things we need to say in terms of the design considerations are that, remember, with the valve, we get to control the sludge age by recirculating the sludge or by discharging the sludge. We get to choose how long the cells are spending inside of the tank. And so if we have a long mean cell residence time, then that means it's going to be more efficient and there's going to be less of a sludge volume that has to be discharged. And so less waste sludge usually translates into a lower disposal cost. It's cheaper. The other advantage of that is that the bugs that are in the treatment plant, when you have a long sludge age, they are sort of more complicated organisms that have the ability to break down nutrients, and the process is called nitrification. If we have not enough nutrients, it's sometimes the case that they need to add a little bit of nitrogen or phosphorus to make sure that the bacteria have everything they need. And so it's sort of like taking multivitamins. You know, I'm sure some people here maybe will take vitamin D or calcium or vitamin C. Once in a while, if the waste that's coming into a treatment plant has plenty of BOD but not enough nutrients, then those nutrients will have to be seeded. And here it shows the optimal ratio of BOD to nutrients for both nitrogen and phosphorus. Heavy metals like mercury or lead can accumulate in the sludge because we're recycling the sludge, as you remember. And so if we know that the stream has heavy metals like that, it has to be, we have to be very careful about making sure that the metals don't accumulate into too high of a concentration in the sludge, because it can be toxic to the bacteria that we're trying to break down. And we also have to be aware of that depending on where we put the sludge. Remember, I showed you a picture of a bag of manure that came from the Dubai municipality. They turn their sludge solids into fertilizer. And so that fertilizer, if it had lead or mercury, wouldn't be appropriate for a food crop. Maybe it would be okay to put it on grass, depending on where the grass was and if animals were going to be eating the grass. But you have to do analysis of the sludge to make sure that the heavy metals haven't accumulated in that sludge. We've already talked about mixed liquor, volatile, suspended solids, mixed liquor, suspended solids. We've discussed the F to M ratio. There's a term that's introduced in the textbook called bulking sludge. And a bulking sludge is something that doesn't settle very well in the clarifier. And there are a couple of reasons why sludge can bulk. Sometimes if the sludge has trapped air in it, then it will float to the top of the clarifier instead of settling to the bottom. And that can be a problem depending on what the microorganism is. Some microorganisms would tend to have long chains and make it more difficult for the sludge particles to settle to the bottom. There are these two terms, extended aeration and high rate aeration, that are at either extreme of the F to M ratio. And so extended aeration means that you have a really long cell residence time, which is corresponding to a low F to M ratio. So lots of bugs, very little food. Remember, they get very efficient and they eat as much as they possibly can. So that gives you a good quality effluent, and there's very little excess sludge. But it means that the tanks have to be larger. High rate aeration, on the other hand, means you're loading down the microorganisms with lots of food. Smaller tanks are required, but the quality of the wastewater coming out isn't as good as it would be with extended aeration. So high rate aeration would maybe be a residence time of between 1 to 3 days. Extended aeration would be more than 5 days in terms of the cell residence time. And remember, the F to M ratios that we saw is between 0.1 to 1. So extended aeration would be 0.1, very little food relative to microorganisms. And the high rate aeration, it would be on the scale of 1, where you have 1 milligram of food for every milligram of microorganism per day. There's a parameter called the sludge volume index that characterizes how easy it is for sludge to settle downward. And the way that that sludge volume index is calculated is that you take a sample from the aeration basin and you put it in a graduated cylinder, which is that glass tube that has all of the markings on it. And then you let a liter of sludge settle for 30 minutes. And what you're measuring is after 30 minutes, as the particles settle down and the clear water stays above, where is the interface between the sludge particles and the clear water? And you'd measure the volume. In 1 liter, maybe you'd measure a certain fraction of that 1 liter is occupied by the sludge. And you can calculate the sludge volume index by this formula. It would be the volume of the sludge that's occupied divided by mixed liquor suspended solids. And the sludge volume index of a typical range would be 80 to 150 milliliters of sludge per gram of MLSS. It's just a test that's done to see if the sludge is bulking, which is when it floats to the top, or if it settles downward, which is what we need it to do. Because if it doesn't settle downward, we can't recirculate it. So this graduated cylinder, in other words, is kind of simulating a clarifier. Okay, this is our top view. It's taking a step back again and remembering everything that happens here. We've talked about how to size the aeration basin. Depending on how much sludge we're wasting, we're going to have to worry about sludge digestion and sludge disposal. And another consideration is how much air should we provide. So when we get together on Thursday, we're going to focus on the air part of it. But for the rest of today, we're going to focus on how much sludge is generated and taking a look at the formulas that tell us for a certain flow rate what's the volume of sludge and what's the concentration of it. Sludge production depends partly on how much food is being removed from the water. And for every kilogram of BOD that gets removed, that leads to 0.4 to 0.6 kilograms of body mass in the bugs. And it also depends on how quickly the cells themselves are dying. The cell death rate influences the sludge production, because if the cells are dying at a high rate, then that's going to increase the mass of solids that need to be disposed of. The observed yield takes that death rate into account. Remember, the yield itself is just for every mass, for every kilogram of food, how much kilogram of body weight do the cells put on. But then the death rate and the cell residence time takes into account the difference between the observed yield and the simple yield. And then this is the formula that tells us the kilograms per day. P sub x has units of kilograms per day of sludge solids that's generated. And it factors in the yield, the flow rate, and then the amount of BOD that's removed. This difference here, S naught minus S, if S naught is the inflow BOD and S is the outflow BOD, the difference between the two is how much food got eaten by the microorganisms. So in the in-class exercise I'd like you to start on, we have an instance where the flow rate is 0.15 cubic meters per second, and we know the effluent concentration from the primary clarifier. We're assuming that this is our S naught into the aeration basin. And then the effluent from the aeration basin is 11.1. So those two parameters are going to fix what we use as S naught and S. And so what we need to do is, for this sludge age of 5 days, and using the typical kinetics parameters, which are on the page, I've provided the typical kinetics parameters on the page, find out what is the mass in terms of kilograms per day for the sludge solids that get produced. Yeah, I changed it to per day because this is asking for the daily mass of sludge. So that tells you kilograms per day. Yeah. No, I multiplied that by 86,400. So the reason why we need to convert the flow rate from 0.15 cubic meters per second to 12,960 cubic meters per day is the problem statement says, what's the daily mass of sludge produced? So volume, Q, needs to be in terms of units of days to find the daily mass. Yes? Yeah. Say theta C at 5 days? Yep, that's the same thing as sludge age. In the problem statement it told us the sludge age is 5 days. And that's kind of a typical value that you'd have your F to M ratio set so that it's a 5-day sludge age. Yes? No, it's, that conversion factor is, there's 10 to the minus third kilograms per gram. So the reason we have that factor is because, yeah, we want to convert it from grams to kilograms per day, right. And you'll notice that here the concentrations that I've put, remember I said in the last class period that milligrams per liter is the same as grams per cubic meter. So I just put 84 and 11, and the units there are grams per cubic meter. But since I want kilograms ultimately, kilograms per day, then I have to divide by 1,000. All right. We are out of time, unfortunately. I'm going to lift up the screen in just a moment so you can copy the rest of that example if you need it. Let me just emphasize, if you didn't take your appointment yet at the Writing Center, go do that as soon as possible. At least make the schedule. Because the last day is November 22nd. You have to have your appointment done by, the last day you can do it is November 22nd. Yes? Sunday, right. Okay. I'll see you on Thursday. Have a good day.